Hello class, this is section 7.5. In this video, we will discuss piecewise continuous function and translation of function about t-axis. Before that, let us recall the unit step function at t equal to a. It's given by u a t or u of t minus a. It is equal to 0 for t is less than a and 1 for t greater than or equal to a. The graph of it looks like this. Suppose this is the t-axis and this is the x-axis, and say this is a. The function is equal to 0 for t less than a, so throughout the left of a it's 0, and at a and after a it's equal to 1. We have seen before that the Laplace transform of the unit step function at t equal to a is equal to e to the power of minus as divided by s, which means that the Laplace transform of the unit step function at a equal to 0 is equal to 1 over s, which means that if you multiply with e to the power of minus as, this corresponds to the translation t going to t minus a. We will now show that this is actually a general property of Laplace transformation. Let us state the following theorem. If the Laplace transform of f of t exists for s greater than c, then the Laplace transform of the function u of t minus a multiplied with f of t minus a is equal to e to the power of minus as f of s, and the Laplace inverse of e to the power of minus as f of s is equal to u of t minus a f of t minus a for s greater than c plus a. Let us first see what does this function u of t minus a times f of t minus a means. So we know that u of t minus a is defined to be equal to 0 for t less than a and equal to 1 for t greater than or equal to a. So u of t minus a multiplied with f of t minus a, it should be equal to 0 for t less than or equal to a, because that's how u of t minus a is defined, and u of t minus a is 1 for t greater than or equal to a, so this multiplication is just the f of t minus a, so it is f of t minus a for t greater than or equal to a. Suppose the graph of f of t for t greater than 0 is given to be this. Say this is the x-axis and this is the t-axis, and suppose this is a. The graph of u of t minus a multiplied with f of t minus a is the translation of this function f by a distance. It's just a copy of f of t, but it is translated by the distance a. So the Laplace inverse of e to the power of minus as f of s is a function whose graph for t greater than or equal to a is translation by a units to the right of the graph of the function f of t. Now let us prove the theorem. From the definition of the Laplace transform, we have the Laplace transform of f of t, which is equal to f of s, is given by integral from 0 to infinity e to the power of minus s tau f of tau d tau. So if we multiply with e to the power of minus as on both sides, we have e to the power of minus as times f of s is e to the power of minus as times the integral 0 to infinity e to the power of minus s tau f of tau d tau. Because e to the power of minus as doesn't contain any tau term, we can safely take this inside the integral and write it 0 to infinity e to the power of minus s times tau plus a f of tau d tau. Now if we substitute tau plus a is equal to t, then e to the power of minus as f of s will be equal to integral from a to infinity. This is because when tau is equal to 0, t is equal to a, and when tau goes to infinity, t also goes to infinity. E to the power of minus s, tau plus a is equal to t, and tau is t minus a. So we have f of t minus a dt. But if we go back and look at the function u of t minus a times f of t minus a, this is actually equal to f of t minus a for t greater than or equal to a. So we can write this as equal to integral 0 to a 0 times e to the power of minus st dt plus integral a to infinity f of t minus a e to the power of minus st dt. Together this will become integral 0 to infinity u of t minus a times f of t minus a multiplied with e to the power of minus st dt, which is the Laplace transform of the function u of t minus a times f of t minus a. This completes the proof of the theorem.